Hello everyone, thank you for coming to my thesis presentation, which is titled Visual Saliency Detection and Semantic Segmentation. So, perceptual grouping has an important role in human visual system, and meaning that human visual system can easily extract high-level information such as structure from low-level primitives such as regions or segments. So, therefore, segmentation, which is dividing an image or video into different homogeneous regions which are non-overlapping, is an important task in computer vision, and it has many applications like recognition, object tracking, matching, and etc. We can group segmentation to 4 different categories. One is generic segmentation, or foreground-background segmentation, salient region detections, and finally semantic segmentation. In this thesis, we use the grouping information in twofold. One is visual saliency detection in videos, and second, semantic segmentation in images. So I have 4 chapters in my thesis. One is visual saliency detection using group LASSO regularization in videos. The second chapter is semantic segmentation or scene labeling using sparse precision matrix, and the third one is scene labeling using knowledge-based rule employing binary integer programming, and finally semi-supervised semantic segmentation using generative adversarial network. The first chapter is visual saliency detection using group LASSO regularization in videos. So the salient data is the most important data in a video, and we want to find the saliency because we want to reduce the amount of information that needs to be processed. So we call something salient if it stands out, meaning that it's different from the rest of the image or the video. For example, in this image, we can easily find out the birds are the salient one, or in this one, the person, and also this one, the boats. So we based our method on the assumption that the salient part of the video or image occupy only a small portion of the video. So we use sparse signal analysis. Now we can represent the information as redundant plus salient or sparse part. Non-salient areas such as background in this representation can be expressed as a low-rank subspace, and salient part can be expressed as a sparse subspace. Also, sparse coding suppresses the slight changes, so the significant changes and variation can stand out. First, for decomposition, we need to have a feature matrix that later on we can decompose it to the low rank and sparse part. So we start with the video clip, then we extract the cuboid, so we can use spatial temporal information. And we build a matrix, we call it observation matrix, that has a low-level features like intensity from the cuboids. Also, simultaneously, we segment the video to some supervoxels. When we have this observation matrix, we can find the bases. We use online learning dictionary. And we can find the groups of those cuboids using these supervoxels. Now, when we have the atoms of dictionary and groups, we can use sparse coding by group LASSO, which the groups are the supervoxels. And when we find the coefficients, we use the coefficient as our feature matrix later on to be decomposed. For decomposition, we use robust PCA. So the sparse matrix, when we find the sparse matrix using robust PCA, we can find the saliency map. So again, when we have this coefficient, it's our feature matrix. We use low rank minimization by robust PCA. We find low rank part and the sparse part. This sparse matrix, it's what we use for finding the saliency map. So for rank minimization, we want to have a feature matrix that we can reconstruct to low rank plus sparse. So minimizing rank is an intractable problem. And also, there is no efficient algorithm to solve the L0 no. Therefore, instead of minimizing rank, we can use nuclear norm, which is an alternative to finding the rank. And also we replace L0 to L1 norm. So our optimization problem would be like this. We minimize the rank of L using nuclear norm and L1 on S, the sparse matrix, in a way that the sum of these two will construct the feature matrix. For feature space selection, we want to use the group lasso because we want to sparse solution that preserve the group of variables together. So we use group regularization, group lasso regularization, which is L1, L2 norm. So given the matrix, and when we assume that we have the dictionary, we use the L1, L2 norm on the coefficients. So this gives us the sparsity among the group. For the bases, we use the learning method to find the dictionary online using the observation matrix, and we can find the D, and we can solve this problem using block coordinate descent. So we tested our method on different data sets. We have 4 different data sets: INB, UCF Sport Action, UCF Saliency, and Hollywood 2 actions. And we report the AUC, area under curve, for raw curve as a metric. Here I'm showing the UCF Sport results. We have different actions like diving, golf, swimming, kicking, lifting, horseback riding, running, and etc. And in the average, we can improve the other methods, which are also unsupervised, about 10%. And interestingly, here, when we use intensity as a low-level feature in observation matrix, we get about 2% more accuracy in terms of AUIC, rather than using just emotion. The second data set is Hollywood data set, which is a movie clip, and we had different actions like answering phone, driving car, eating, fighting, and so on. And on average, again, we can improve the other methods like Sunday and Bayesian surprise. Also here we use the idea of this. We have a smoothing over the center of the scene because these are from the movies. So using this smoothing, we can further improve the result by 6%. To show the effectiveness of our method, besides just finding the visual saliency, we use this saliency maps to discard some descriptor, and then we apply this on action recognition. For this, we use HUG and MBH descriptor. For the baseline is when we use all descriptor from all the video. And for saliency sampling, we discard about 30% of descriptor that belong to non-salient part of the video. As you can see, in average, we can improve the result by 5%, and for some actions, we get like 50%, like running. So for finding the visual saliency in videos, 2 things are important. One is objects, one is motion. So using this approach, we can capture those parts of the videos. And also grouping information can help that we don't split the objects. These are more results that we can predict the eye movement. The regions that those red dots are the eye movement and the gaze from viewers, and these are the segmented, after thresholding the saliency map, we have this 0-1 segmentation. In summary, this is a summary of this chapter. We propose a completely unsupervised method to detect salient regions in videos, and we use spatial temporal information to represent a video as a matrix. Then we use supervoxels to cluster those data and use the grouping information to group in group lasso coding. Also, we decompose this feature using the robust PCA, and we can get the saliency out of the sparse matrix. So the first part is saliency detection, which highlights only important region in the video. And in saliency, there is no notion of classes, but when we want to address the problem of semantic segmentation, which we label each pixel, this is a richer representation, and this kind of analysis provides more understanding of the image because we have labels for each region. The first work on semantic segmentation is scene labeling using sparse precision matrix. So the goal of semantic segmentation is assigning a semantic label to each pixel. For example, given these images and a set of labels like car, building, trees, we want to come up with these segmented maps which each pixel has a label. This is a challenging task because it contains recognition as well as segmentation. Some typical approaches, they start with segmenting the image into superpixels or segments. Then they have these local features and using some classifiers to label each superpixel using the local features. And also on top of that, we have some smoothing in a way that neighboring segments get similar or same labels. These approaches, they have some limitation. First, they ignore to incorporate long-range connection between the superpixels. Also, they don't model this context that belong to how labels interact each other and the relationship between labels. So in our approach, we want to model and capture interaction between labels as well as between segments. For that, we use the energy minimization over a graph, which this graph can be found using inverse of covariance matrix that called precision matrix. And so using this graph, which is sparse, we only encode the significant interactions, and we avoid fully connected graph. In this approach, we use local plus global information. Here I'm talking about some background that might be useful for the rest of the chapter. So the first thing is covariance, which is very familiar, and it defines using expectation and measures how two variables changes together or covary. The second one is correlation, which is covariance that is normalized by standard deviation and measures how it's a more proper measure to comparing two variables because it's normalized between -1 and 1. And the second one is precision matrix, which is the inverse of covariance matrix and measures how the variables are not covary or how they are independent. And finally, partial correlation, which measures the degree of association between two random variables given other variables. So the partial correlation and the precision matrix, they have this useful relationship that we want to use that, meaning that the precision matrix for two variables, if it's 0, it means that these two variables, if they are partially uncorrelated given other variables. And we can use this to find the conditional independence in a graph. If we want to use sample covariance, it might not be a good idea to find the precision matrix. First, it might not be invertible. Also, even if the covariance is invertible, it might be noisy. We want to have a sparse matrix that we can find a sparse graph. So for that, we use graphical lasso for estimating the precision matrix. That this is the penalized log likelihood or L1 regularization of the log determinant problem. So by adding the L1 constraint on this omega, which is a precision matrix, we can capture the significant interactions and find the conditional independency between variables if we assume the distribution is Gaussian. Now, when we have the sparse precision matrix, we can find the structure of dependency of graph between variables, and when there is 0, it means there is no edge. So in training, we start with segmenting all training examples and find features like local features like SIFT, color histogram, etc. for each superpixel. Then we train local classifiers on those superpixels using random forest. Also, here we use some global information as well. We use gist feature for a query, and when we find the retrieval set for that image based on the gist feature. In addition, in training, we find the label graph. Label graph encodes the relationship between labels and the partial correlation between labels that later on in inference we use this for pairwise cost. So how we can find the label graph? If we have this training example, the images, we build a data matrix which each column belongs to one image and each value is the probability of seeing specific label or the frequency of that label in that image. So we have a L by N matrix. And then we can use graphical lasso to find the precision matrix, which is sparse. Using the precision matrix, we can build the label graph using the correlation. When we have this label graph, we can find how these labels influence each other, and we use this partial correlation in pairwise cost. Now, the other way that we use graphical lasso is to find the scene graph. Scene graph captures the structure of graph among superpixels. So now each superpixel is treated as a random variable. We can use the feature of it or the results of the classifier of that superpixel to find how this superpixel are connected. Then again we use graphical lasso to find the partial correlation, and 0 means no edge, now between superpixels. And now we have the dependency between superpixels. So in inference part, again, when we have an image, we segment this image, the query image, and we compute the features. We find the interaction between superpixels. So this is our scene graph. We build the optimization over this graph. So for unit return for this graph came from the classifier. And also we refine the local classifier scores by using this retrieval set using the gist features. And we compute pairwise cost between the connection. For the pairwise cost, we use the label graph that we found in training in addition to some appearance features from the image. Then when we optimize this energy function, we can get the final result, which is a semantically segmented image. So for energy function optimization, we have this energy function, which has this unary term and the pairwise term. The unary term is a simply sigmoid function over the refined confidence scores from classifiers. And the pairwise term has two terms. One is delta, which encodes the correlation between labels. This row comes from the precision matrix of label graph that we found in training. And also F has two parts. One is finding the dependency between superpixels using the appearance of them and the position of them. Also R, it's measures how this superpixel correlated using the scene graph. Then we can easily use alpha expansion, for example, and optimize this energy function and find the labels. We tested this method on different data sets. The first one is SIFT flow data set. On the left, I'm showing the label graph if you just use the practical covariance matrix and just inverse that. As you can see, it's very noisy, and we don't want to have a fully connected graph for this. We just want to encode the significant interaction. So on the right, this is the label graph that we found using the graphical lasso, and it's kind of meaningful, and it has just significant interaction. For example, here you can see car and road, they have high correlation, or street light and crosswalk. So when we use this method, starting from, if you just use local classifier, we get 71% accuracy. Using the global, we can improve it. And again, spatial smoothing, you can improve a little bit more. And finally, using the sparse structure, we can get about 9% accuracy over the local classifier. And these are the methods that we compare with. The second data set is Stanford background data set. Again, if we just use local classifier, we get about 73. Use global information here helps more. But spatial smoothing again helps a little, but using the sparse structure, we get better results. And these are other methods results. These are some qualitative results to show how this connection can help. This is an image. This is a classifier output. This segment is incorrectly labeled as building. It should be road. When we use spatial smoothing, even it's over-smoothed it. But when we have this long-range connection, we can refine that and avoid over-smoothing, and we get the segment correctly as road. These are more examples. For example, here we can get the bus better. Or here the trees, even though they are far from each other, but they can have this connection, so we can avoid over-smoothing by changing the pairwise cost, and we get better results. The other important thing is how the labels can influence each other and affect the pairwise cost. So this is again an image that the classifier gets some false positives, and even spatial smoothing can help, but still we have some segments incorrectly labeled, but we have this mountain road correlation which gives us higher cost. Then we can smooth out that part. On the other hand, when we have this image which has door and building, spatial smoothing over-smoothed that the building has more score, but when we have building door positive correlation, the pairwise cost reduced, so we can avoid over-smoothing and keep the door segments correctly. So the summary of the chapter is we find the dependency and interaction between labels as well as superpixel using sparse precision matrix. We use global information as well. Also, we want to take into account long-range connection, and by using this approach and the graphical lasso, we can avoid over-smoothing, and we don't need a fully connected graph to capture those long-range connections. The third approach is scene labeling using knowledge-based rules, employing constant integer programming. Here we want to leverage some knowledge-based rules to pruning the search space for the assigning the labels. So if we have a simple classifier, we want to use this knowledge models constraint in inference part to refine those classifier scores. For the classification, we use superpixel classification. Also, we use some global information. So in inference, we have this problem, which W are the scores, and Y's are the binary variables, meaning if this superpixel can get a specific label or not. And the first constraint is that for each superpixel, we should have only one label. So the sum of this for one superpixel should be 1. These are some examples for the motivation behind this idea. This is a sample image and the ground truth. We have some rules, for example, sea and sand, they co-occur, or there's no road above sea. So when the classifier incorrectly segments its part as road, using this rule, we can refine it and capture the sand. Also here, these are the image and the ground truth, so we have some rules. And when we have no car above sea, this example, which is car, can be refined and we can get the mountain correctly. So for this approach, we start again with segmenting the image. We have to have a label for each superpixel. So for that, we use local features and XGBoost classifier. Also, we use global information from scene label association that I will talk about that later. So when we have these two, we can have a score or those W's in our formulation. Now from the training data, we extract some expressive rules. So we have these knowledge-based rules, and we convert these rules into constraint that later on we can apply it in integer programming. So when we have this constraint from rules and we have the classifier scores, we can use the idea of the product of the expert and define our problem as a binary integer problem with constraint. When we solve this, we can have a label for each superpixel in a way that these assignments satisfy the constraint. Then we get the final result. For finding the feature scores, we can use the local classifiers. We segment images and we compute the feature vectors for each superpixel, and we apply XGBoost to, we train XGBoost to have the category for each superpixel. Also here we want to use global information because it's in performing scene labeling, using scene information can be helpful. For example, if you know the scene is a restaurant, the probability of seeing semantic label like cherry would be high, or if it's a desert, the probability of seeing river, it's low. So we want to use this idea. For that, we use this places network that they trained it on more than 200 scene categories. They are just for one image, the label, the categories. So how we can use this global information? We want to find a mapping between these scene categories and the semantic labels. For that, we use this non-negative sparse regression. So when we want to learn the mapping between categories and scenes, so when we have V is a matrix of occurrence of the semantic labels in our training data. And we want to find U, which is a weight matrix, and we can have S from the scene confidences from the places. When we learn this U, we can later on use that in the inference part. So in inference, we use the local classifier to obtain the local confidence vector for each superpixel. We call that WL. Then we use the places model to achieve this scene category for the whole image, SI. When we have U now, this is a scene, this is just a weight matrix to map this scene categories to semantic labels. Then we have the global label confidence for superpixels. And by late fusion, we can refine the scores. Now we have the classifier scores. For the rules, we define some rules. This, for example, co-occurrence, like face and body, or car and road. Non-coexistent, for example, book or car, the books are in the library, and etc. And we have special rules like sky above, grass, road below building, and presence, which is like pole and road. If you see pole, you have to have road, or you see balcony, you have to have building. When we have the rules, we need to convert them to constraint. So the first one is special constraint. It means that whether two labels can have a specific special relationship or not. For example, sky is always seen above the sea. If the label for a superpixel has this specific label, for example, if this is sea, so the superpixel below that cannot be sky. We can convert it in this inequality binary integer programming. If this is 1, the sum of others should be 0. The second one is mutually exclusive or non-coexistence. So these never occur together. If there's a superpixel which has a label like C, it should not be any superpixel with desert. So the multiplication of the sum of them should be 0. If one of them is 1, all of the other variables should be 0. The third one is presence. that if we have a certain label, it should have at least one of the superpixel with other label. For example, if you see balcony, you have to have at least one region with building label. So if one of them is 1, at least one of the others, the sum of others should be 1. This is the inequality for this rule. Now we have to find the labels that they follow those rules. For this, we use the training data to find the frequency or probability of each rule for each pair of label. We have two kind of constraints. One is hard, which this pair of labels strictly follows those rules. The other one is soft, that for the soft constraint, we allow some degree of violation. So now we have integer programming with soft constraint. We use this 0-1 constraint modeling. So this part is what we have as a scores and the binary variables. For this, we have this extra zk, the variable, which is equivalent to a conditional constraint. If constraint k is violated, z will be 0. Then when it's 0, we apply this penalty pk. And we find the value of penalty using the probability of violating or satisfying the constraint in training data. We applied this method on different data set. The first one is Tiflo data set. Using the local feature and classifier, we get 72. Using this global information from places, again, we improve it. And using the rules, we can improve it further. These are some qualitative results. This is a human annotation. This is local classifier. Global classifier can somehow refine it. But using this rules, we can refine it further. And also here, for example, we have these rules, no sky below C. We can refine this part and get better results. And this is the example with the car above C, and we can refine it and get the better qualitative results. Sorry. Excuse me. So the second data set is MSR-CV2, which has 23 labels. We use this we have very few training labels here. We have just around 200. So these rules can be helpful. These are the other methods that they somehow use the idea of the co-occurrence, but not other rules. So here, local classifier gets 76. Using global context, we can improve it, and with the rules, we can get better results. These are qualitative results for MSR-CV dataset. This is the ground truth. This is what the local classifier gives us, which is very noisy, but using this rule, we can get rid of most of those false positive and get better segmentation results. The last data set in this chapter is LMSUN data set, which has about 200 classes. And the local feature and classifier gives 53, using global information 57, and using the rules we get improvement about 4%. And rules here are very important because we have just few examples for each class. These are the per pixel and per class accuracy for LMSUN dataset comparing with other methods. As you can see, we get better results in terms of both per pixel and per class accuracy. In summary, in this chapter, we want to leverage from global context, and also we use this enhanced inference method that enables to model incorporate this expressive rules. And we apply integer programming formulation. We get the soft constraint in addition to hard constraint. They're using soft constraint make our model more flexible. So these methods that I was talking about, they all are fully supervised. And the presented approaches for semantic segmentation, when they are fully supervised, they need lots of annotation data, but the annotation data, annotated data for supervised method in terms of semantic segmentation is expensive because you have to label each pixel. So in the next chapters, we want to use generative adversarial network to have a semi-supervised method, to use either unlabeled data or weakly labeled data in addition to fully labeled data. So the title is Semi-Supervised Semantic Segmentation Using Generative Adversarial Networks. If we, so as I said, we have this lack of annotation for semantic segmentation, but on the other hand, we have lots of unlabeled data, and we want to use a generative model to improve the classifier. So if we have this labeled data, and we can train our model to get using a supervised loss, now when we have unlabeled data and the generated data, we can use this data in a semi-supervised fashion to improve the classifier results and get the final result better. So an alternative to supervised learning is unsupervised learning. But unsupervised learning has not been very successful in semantic segmentation because they just want to keep the structure of the data and find the consistent regions. But here we want to use semi-supervised learning, which is a halfway between supervised and unsupervised learning. So we use the assumption of this smoothness constraint, which is if two data points lying in the same manifold in the first space, when you map them to the second space, which in our case is a segmented space, if in the first space they are closed, in the second space should be closed, or they are likely to be classified in the same cluster or the class. So we want to leverage the unlabeled data to find this structure. Generative model can learn representation that are predictive of high-level concept. For example, from some handwritten digit, you can find the number. And for the cost, we have this loss for the supervised and for the unsupervised. And this unsupervised data can play a role like a regularization. So we have generalization. We can avoid overfitting. For the unsupervised method that can help, I'm using generative adversarial network. So this is just an introduction to what is GAN, or generative adversarial network. This is just an intuition behind that. For example, if you assume you have a painter who wants to do art forgery, we call this G. And we have someone like some art critic that judging these paintings, we call that D. So G produced some paintings to fool D, and so D needs to start learning more, for example, about Picasso to can tell apart what is real or not, and G has a harder time to fool D. In this process, D gets really into telling apart what is Picasso or not. Also, G gets really good at painting the paintings that look like Picasso's painting. So the idea is in this process, both get better. This is an example from typical GAN for ImageNet, which we have G, the generator, and D here. D is just binary classifier that it says the data from the training data is real, and the data from generator, which is these are the samples from generator, are not real. So the formulation of GAN is we have this constant competition between two networks. So because of that, they call it adversarial. So G starts from noise and generated images. We call it G of Z. And D takes these images from G, also the images from the real distribution. And Dx is the output of discriminator for the real data, and D of G of Z is the output of discriminator for the generated data. Then they play a min-max game between one another. And the idea here is discriminator is optimized in a way that the probability of being real for those training data should be high, and the probability of the generated data being real low. This is like an EM-like algorithm. Iteratively, they optimized.
You want to go through each term, say what these do,
Sorry. So dx is the output of the discriminator for x, the real data, and dgz, z is the noise, gz it's the generated data, and dgz is the output of discriminator for unreal data or the fake data. So we want to maximize over d. So the probability of this should be high, and the probability of being real for gz should be low. But on the other hand, we want to minimize this over g. So the g needs to generate the images that they look like real, and probability of being real for those images should be high. So now we want to use GANs in a semi-supervised fashion. So this is like, we can say that this adversarial loss is somehow better than other loss for generative models. So we want to leverage from unlabeled data by estimating a proper prior. Then this prior is used to improve the classifier. So in GAN, we want to have a result that unlabeled data, because they belong to the same distribution of the labeled data, we have to have an objective that for this, for the unlabeled data would be low, but for the generated data should be high, because the assumption of the generative model is to find that objective, that the data which belong to the same manifold, the objective should be low, but those that they are found from that manifold, which they call it contrastive points, they should be high, the objective function. So the generated data should not belong to the same distribution. So this is, if we, this is the typical configuration for for semantic segmentation networks, that you have some labeled data and you have the discriminator, which in our case, I have to mention that we replace the binary classifier with a fully convolutional neural network that does the semantic segmentation. So it produced the probability map for each class. Now in a semi-supervised fashion, we have the unlabeled data and the fake data. So we had this extra fake class. So here, the idea is that when we have this generated data, the generator tries to confuse D. Now D needs to learn more robust features to be able to distinguish between this data and the generated data. So applying the same filters from the discriminator should have the similar categories for the unlabeled and labeled data, but they have to be far, and they have to be fake for the generated data. For the generated network, we start with the noise, and we followed by the convolution layer, and we get this generated image.
The output is the generated images, not the generated discrimination.
Yes. So for the discriminated loss, we have the unlabeled data loss, supervised loss, and the fake or generated loss belong to data distribution. So this is the loss for the unlabeled data, this is for the cross entropy, and this is for the generated data.
So the fake label is assigned to the whole image, or?
For this is, I have to say, this is a pixel level.
Things that have fake labels.
Yes. So generated should try to generate samples close to real data. So it should minimize this formulation or equivalently maximize the being real for those pixels. Then when we have this alternative gradient optimization, these two networks using this formulation and the batch of the real, the batches of the real and generated data, again will slowly converge and producing some realistic data, but in the same time the discriminator gets better. Okay, so we extend this idea of the semi-supervised to weakly labeled data. Now we have the classes, the class information of the image, not the location of them. So we use a conditional GAN to condition the generating on those classes. Also, we use the image label in the unlabeled data. Now we change the, we have this conditional GAN, and we change the formulation. We have the L, the extra information here in conditional GAN, which is a class label. And in the discriminator loss, now we have the classes. So here we say we have only those, we should have those classes in the unlabeled data. The rest is the same. So we have tested this method on different data sets, Pascal, CFlow, Stanford background, and CAMVID, and we evaluated using different metrics, pixel accuracy, class accuracy, and average of region interaction over union, or IU. This is the result for the Stanford background. We compared with this reference number 15. They used the idea of generating segmentation using the GAN instead of using this semi-supervised approach. As you can see, we get better improvement because the semantic segmentation is a complex task, and we use this fully convolutional neural network, but we just use GAN as an auxiliary to help this classifier. And this is the result for CAMVID. CAMVID is a good fit here because it's a long video, only 700 of them are labeled. So we can get good accuracy, especially in mean accuracy results. These are some qualitative results for Stanford background. As you can see, the foreground object can be captured better. So we have the images again for this Stanford background data set. This is a quantitative result on Pascal. We get, for the Pascal, we can use weakly supervised approach as well because we have the image level label, and we get some improvement. We repeated this experiment with using only 30% of the label data, and using the weakly supervised, we can get improvement also. These are some quantitative results if we just use 30%, about 400 of the labeled data. This is for the class supervised, this is semi-supervised, and the weakly supervised. You can see we can get better maps. And this is the result for CFlow dataset. CFlow dataset doesn't have more unlabeled data, but we use SUN because the CFlow is a part of SUN dataset. So, and we get some improvement again over just using those fully labeled data. And these are examples from CFlow, which has a better accuracy per class. For example, some classes like person here cannot be found here, but here we can find the person. And these are some generated images. This is like sea and sky from CFlow. This is forest or like dog and cars and vases. Even though our goal is not produce very realistic generated data, but these are also meaningful. So summary of chapter is we propose a novel semi-supervised semantic segmentation. We use GAN. Also, we extended this using the weakly labeled data to have a weakly supervised approach. Our model generates meaningful synthetic images as well. So these are some comparison of the methods that I proposed. So for example, graphical LASSO was a plausible math model, but in the knowledge-based rule, we use this expressive model, but it has, we use visual features and high-level information based and convert those to constraint. But in both cases, we can find some relevant information about data. For example, special relationship can be learned implicitly in graphical LASSO and explicitly in the rules. In terms of results, the class accuracy for rule-based method gives better results. And for larger data set, for example, LMSUN, when there is not enough data for some classes, rules also can be helpful. In terms of complexity, there are many optimization methods for CRF, like alpha expansion, etc. But for binary integer programming, they have some limitation in terms of number of variables and the time complexity. However, for binary integer programming, also you can use some tools and you can convert them to simple constant as well. For the future work, in the first approaches, we use superpixel or supervoxel segmentation. In both cases, if you have a better solution for supervoxel or superpixel, can improve the results. Also, we use so-called handcrafted features like saved color histogram. Using some recent approaches to find the features can also help. Even though the CNN, the CNN methods can lose some context information, maybe because of the pooling or because of the receptive field. So some methods, like graphical LASSO or other methods that they can somehow infuse the context, can help the results. Also, this rule-based method that we use can be applied in a weakly supervised. If you just have labels, you can use this idea and guide the semantic segmentation for each pixel. In the GAN approach, we just replace the discriminator with simple, fully convolutional neural network, but using more recent approaches like ResNet can help. And if you want to have more realistic data, we can have another branch for just binary classification. Also, for the weakly supervised, we can combine the bounding boxes or use some foreground, background scores. These are the papers that I published, and I used them for this thesis.